Hello everyone, my name is Varun Ranganathan and I am a master student at the University of Alberta. Today I'll be presenting GrCluster, a scope function to model hierarchy in knowledge graph embeddings. Knowledge graphs are data structures that store facts of the world in the form of RDF triples. These facts contain properties of real world entities and their relationships with other entities. Applications like question answering rely on knowledge graphs. These knowledge graphs should be large and accurate. But knowledge graphs are incomplete, since the state of the art IE algorithms are not sophisticated enough to understand natural language over the web. To this end, knowledge graph completion is a direction of research that aims to find new facts based on the facts that are already present in the KG. These tasks has been dominated by KG embedding models, which aim to find vectors for entities and relationships present in the knowledge graph while preserving the latent structure of the knowledge graph. Most KG embedding methods ignore the inherent hierarchy of entities. Our idea is to improve the robustness of KG embeddings by explicitly incorporating the entity hierarchical information. Therefore, we introduce the GrCluster score function. GrCluster is simple, intuitive, and efficient. Simple because it is easy to incorporate into the objective function of any knowledge graph embedding technique. Intuitive since it encodes the entity hierarchical information in terms of distance. Efficient as it employs only a single parameter over the baseline KG embedding technique. We play with several well-known KG embedding techniques. The embeddings obtained upon using GrCluster show consistent improvements in the standard KG completion task of entity prediction and triplet classification. Let me introduce some background and related work. There are two types of KG embedding techniques: semantic matching models and translational distance models. Semantic matching models use similarity based objective functions which measure the probability that a fact exists in the KG. This is done by matching characteristics of entities which are encoded in their vectors. Our experiments involve three semantic matching models: Dismut, Complex, and Holly. Translational distance models use distance based objective functions that aim to minimize the distance between two related entities. Distance is computed by a translation operation performed by the relation involved. Our experiments include trans E, trans H, trans R, and trans D. There are few work related to GrCluster. Type embodied knowledge representation learning, or TKRL, can be viewed as a simplified version of trans R. This is a translational distance model in which an entity can be associated with several types. Type-specific projection matrices are constructed by hierarchical type encoders. Due to matrix vector multiplication and the training of hierarchical type encoders, this method cannot be used to scale to large KGs. KG embedding with hierarchical relation structure, a work by Zhang et al., introduced a novel scoring function that encodes relation hierarchical structure into relation embeddings. GrCluster follows a similar intuition, but for entities. Poincare embeddings operate on the hyperbolic space rather than the Euclidean space. This technique places entities that are higher up in the hierarchy closer to the origin. Hyperbolic entailment cones overcome the problem of asymmetric relations by proposing an efficient algorithm to learn hierarchical embeddings of a directed acyclic graph. These two embeddings techniques, Poincare embeddings and the hyperbolic entailment cones, do not support relations other than the parent-child relationship. Now I would like to introduce GrCluster with its motivations and derivation. The first motivation of GrCluster is that hierarchical relationships are very common in KGs. Incompleteness of KGs may affect modeling entity hierarchies, resulting in a compromised performance. For example, let us look at a small portion of a sample KG. There are four facts: cat subpart of domesticated pet, cat plays with dog, cat plays with human, dog subpart of domesticated pet. If the last fact was missing from the KG, the embeddings obtained for dog would be similar to the embedding for human than cat or domesticated pet, resulting in an incorrect modeling of the world. Our second motivation is derived from the object oriented programming paradigm. There is a rule in OOP that states that an instance of a child class can be used anywhere an instance of its ancestor class can be used. We adopt this to the setting of KGs. A child entity can replace a parent entity in any fact without changing the semantics. For example, an entity red car can replace car without changing semantics, but not vice versa. I will come to that in a minute. Now, the parent entity car can be looked as a representative for all its entity descendant entities. Car equals red car. The distance between the red car and car should be 0. There is another rule in OOP. An instance of the parent class cannot be cast as an instance of its child class. This is because the child class may have some additional characteristics that is not modeled by the parent class. For example, entity ball cannot in general substitute another entity golf ball without changing the meaning. There is some dissimilarity which can be illustrated through the construct of distance. The golf ball is not equal to ball, there is some distance between golf ball and ball. We measure this distance as a function of the number of edges between them in the entity hierarchy tree. Let us introduce the term discount factor. We denote discount factor with gamma. Discount factor gamma is a similarity between two entities connected by a single edge in the entity hierarchy tree. We would like to constrain discount factor to be between 0 and 1. Let phi be a function that represents the similarity between any two entities connected by d edges. We decompose phi as a recursive function. Phi gamma d is equal to phi gamma 1 into phi gamma d minus 1. By the definition of discount factor, phi gamma 1 is equal to gamma. We further decompose phi gamma d minus 1 in a similar fashion. In the end, phi gamma d is equal to gamma to the power d phi gamma 0. If the two entities in question are the same, there will be no edges between them. Therefore, phi gamma 0 equals 1. For two disconnected entities, we assume that gamma d tends to infinity. Therefore, phi gamma infinity is equal to gamma to the power infinity, which is equal to 0, because gamma is a value between 0 and 1. Let phi prime gamma d be the distance measure. Phi prime gamma d is equal to 1 minus phi gamma d. We would like the hierarchical information to be encoded over all dimensions of the relation vector. For this, we employ a scalar matching operation. The distance between two entities in all dimensions should be equal to the hierarchical distance. The GrCluster score function can be described as the positive part of the difference between the average value of the relation vector and phi prime gamma d. The positive part function follows from the second motivation, that a parent entity can be replaced by its child entity but not vice versa. Since the relation is used to compare the entities of a fact, we would like to backpropagate the entity hierarchical information through the relation vector and into the entity embeddings. There are two variants of the GrCluster: hyperparameterized and parameterized. In the hyperparameterized version, the practitioner sets the value for the discount factor. In the parameterized version, a sigmoid activated tradable parameter is used where gamma equals theta, which is learned through gradient descent. The GrCluster score function can simply be added to the objective function of any knowledge graph embedding technique. To evaluate the performance of GrCluster, we chose two standard KG completion tasks of entity prediction and triplet classification. Two standard datasets were chosen, the Virginia hierarchy and WN18. Standard metrics were used to compare performances with baseline KG embedding techniques. The supplementary material contains the code and the generated embeddings. The first experiment involves wordnet hierarchy with Transy. We wanted to observe the performance of GrCluster in modeling only hierarchy. Since the dataset contained only one relationship, it was decided that we would use the Transy embedding technique. Since a parent entity might have several child entities, the task was to predict the parent entity given the child entity. Table 2 from the paper shows the results of this experiment. We prefix GR for those models that have been trained with the GrCluster score function. It was observed that the models that have been trained with the GR score function was able to outperform the baseline Transy model on both the tasks. Table 3 shows the ranks predicted by Transy of the parent entity given the child entity. For the child entity American lobster, Transy predicted the parent entity as physical entity at rank 1, entity at rank 2, matter at rank 3, solid at rank 4, and finally the correct parent entity, food, at rank 5. All of the entities at the first four ranks might be correct. They are ancestors of American lobster. On the other hand, GR Transy was able to perfectly identify the correct parent entity. This is similar with the other examples shown. In the next experiment, we wanted to show how GrCluster performed when multiple relations were involved. The Transy embedding technique is known to have poor performance for modeling relations of the type 1:n, n:1, and n:n. Table 4 from the paper shows how GrCluster model performs against the baseline Transy model. An improvement can be observed, especially on the n side of relations. GR, GR Transy with a discount factor of 0.5 was able to outperform the baseline Transy in the task of entry prediction across all relation types. We incorporated GrCluster into four translational distance models to evaluate its performance. Table 5 displays the results from these experiments. It can be observed that models trained with the GrCluster perform better in both KG completion tasks. The improvement in performance was observed when models were trained with the uniform negative sampling technique and the Bernoulli negative sampling technique. Similar improvements in relation types, such as in Table 4, was observed with all other models. To further illustrate the effectiveness of GrCluster, we chose three well-known semantic matching models. Table 6 shows the consistent improvement in performance of embedding techniques when the GrCluster scoring function has been incorporated to the objective function of the model. Both the parameterized and the hyperparameterized variants of GrCluster improve the baseline KG embedding model. In conclusion, we have presented a novel scoring function called GrCluster. GrCluster is a score function that models the entity hierarchical correlation into knowledge graph embeddings. It can be incorporated into the objective function of any KG embedding technique. It employs only one additional parameter and is able to generate more robust embeddings. Embeddings generated were evaluated on two standard KG completion tasks. KG embedding methods consistently showed improved performances when including the GrCluster score function. Thank you. Have a good day.